In section 5.5, we'll be finding the area of a disk. All right, so this is example 5.5.1. I want to find the area of a disk of radius 1. All right, so here's the formula that you've seen in high school. A disk is given by x squared plus y squared is equal to 1. All right, so the first step in either using horizontal or vertical slicing will be to isolate one of them. So I'm going to isolate y. So here, I'll get that y squared is 1 minus x squared, and so y is plus or minus root of 1 minus x squared. Right, so I have two different curves. Let me put them in blue and green like we usually do. I have, well, for y is positive root, I'm going to get positive number, so that's going to be this one. And then for y, which is the negative, I'm going to be with negative values of y, so it's going to be right here. All right, good. So when we set up the integral, we'll have top minus bottom as usual. And so the area would be the integral, oh, I need the bounds as well, but let's say AB top minus bottom. I'm using vertical slice because I'm isolating y. But let me say horizontal slices would be exactly the same level. So top is always the blue, bottom is always the green. So I will get the integral of top, which is root of 1 minus x squared, and then minus root of 1 minus x squared dx. That will give you the integral of 2 root of 1 minus x squared. Excellent. I need bounds. So when I'm using horizontal slicing, since my when I'm using vertical slicing, since my variable is x, the bounds should be telling me which values of x I'm considering. And so here, these points we know. It's a circle of radius 1, so I'm 1 away from the center, which is 0, 0. So it's minus 1 and 1. So minus 1, 1, minus 1 and 1. All right, so now we have to integrate 2 times root of 1 minus x squared dx. It's not an integral that we know how to do. The only thing I would try is I would say, well, take this to be u, but then du will be 2x dx, and I don't have an x in front, and so the x would stay, and then it would be a mess. And so I will not use a substitution like that here. In fact, I will use a strange substitution. So I'm going to give it a light bulb because this is a bright idea that I wouldn't expect everybody to think of. I have this square root, and it's a lot like the square root in the derivative of arc sine. And so I'm going to try theta equals arc sine of x. It seems a bit crazy because it's not a function that I have at all in my integral, and it's not even its derivative that I have. I have something that looks like its derivative. All right, but then the derivative is square root of 1 minus x squared dx, and so I would get dx as square root of 1 minus x squared d theta. All right, so let's, wait. Oh, that's right. All right, so my area would be twice. I still have square root of 1 minus x squared. Then the dx is square root of 1 minus x squared d theta. And so I would get well, let's take the 2 out. I would get 1 minus x squared d theta. So I would need to be able to rewrite this in terms of theta for this substitution to work. Well, it turns out it's going to work, because in this, I can actually isolate x. If theta is arcsine of x, well then x is sine of theta, right? Their inverse function. And so what I'll get here is I will get 2 the integral of 1 minus sine squared theta d theta, and I'll take an extra step and write it as cosine square theta, because that's what we'll have in our method that we'll see next section. Right, so the substitution worked. I got from an integral I didn't know how to compute to something that we're comfortable with. We spent all this time learning how to integrate powers of trig functions. I'm going to just apply an identity here. I still need to worry about the bounds. So I need to apply this function to -1, and I need to apply the same function to 1. So I'm going to get arcsine of -1 and arcsine of 1. Arcsine of -1, that's, I mean, you could ask your calculator, but you should know by now it's minus pi on 2, and then on top it's pi on 2. So those are the bounds I have, minus pi on 2, pi on 2. All right, let's finish this integral. Because I have an even number of cosine, no sines at all, I'm going to use this power reducing integral like that, formula like this, and then the 2's will cancel, so I'll end up with the integral from minus pi on 2 to pi on 2 of 1 plus cosine 2 theta d theta, and I get theta plus, and then the integral of cosine is sine, but I have an extra 2, so I need to divide by 2 from minus pi on 2 to pi on 2. All right, I get pi on 2 plus sine of pi over 2 minus pi on 2 plus sine of minus pi over 2. Sine of pi is 0. Sine of minus pi is 0. So this is 0. That's 0. And so I get pi on 2 plus pi on 2. I get pi. What did we get? We got pi. What does it mean? Oh, wait. So what we just proved is that the area of a disk of radius 1 is pi. Usually you get pi r squared, the r is 1, it matches. In fact, you could do exactly the same reasoning for any radius. You could even call the radius r, you'll just get r squared here. The same reasoning would work and you would get pi r squared. So this is a way of proving that formula for area of a disk that you've seen so much before. All right, let me say this idea wasn't obvious and it still isn't quite clear when you should use it and how to use it. So that's what we'll spend the next chapter in. In chapter 6, we will study how to use these substitution of inverse trigonometric functions to evaluate integrals which contains the following roots. So we'll use it for, well, we had 1 minus x squared, but we'll use it for a squared minus x squared, and we'll use it for root of a squared plus x squared as well.